Hi, I'm Zhiying. Today I'm going to talk about DeDe, which scales resource allocation through the idea of decouple and decompose. I did this work during my PhD at Harvard, together with my advisor Minlan and Francis from UIUC. Nowadays, network systems are getting significantly large and diverse. For example, clusters now have thousands of computing resources of different types to share among tenants, including all sorts of GPUs, CPUs, and other computing resources. Another example is a wide area network with hundreds of network links to carry network flow across data centers all over the world. Each link has different bandwidth capacities. With so many diverse resources, how do we efficiently share them? Systems rely on resource allocation to meet dynamic user demands, such as allocating GPUs to computing jobs. This kind of allocation is often modeled as an optimization problem, such as linear programming or mixed integer programming. Given an optimization objective and constraints, a resource allocator needs to figure out how to assign resources to demands. However, as the system gets larger and more diverse, it could take hours to find the optimal allocation, making it hard to meet the service requirement at scale. To address the scalability crisis, current method trades off between computational speed and allocation quality. Optimization solvers like Ruby can find the best solution, but they can be too slow at a large scale. To speed things up, people have tried heuristics, approximation algorithms, and ML-based methods, but these usually give suboptimal results. Besides, these approaches are often domain-specific or workload-dependent. Therefore, our goal is to build a general-purpose resource allocation framework that is both fast and high quality. To this end, we surveyed dozens of real-world resource allocation problems in recent literature, and we found that they all share a common separable structure. Let me explain what I mean by separable using a small example in cluster scheduling. In this example, every hour we need to decide how to allocate 3 machine learning jobs on 3 types of GPU, such as A100, H100, and V100. Each job can split their runtime across different GPU types, and we use the X to represent the fraction of the hour a job runs on a GPU. Naturally, we have per demand constraints on each column of X, where the sum of runtime for each job cannot exceed 1 hour. On the other hand, for each GPU type, the total GPU hour requested by all jobs must stay within the capacity of that GPU type. This per resource constraint applies on each row of X. Since each GPU have different specs, a job can achieve different throughput on each type. And the objective is to maximizing the total throughput across all jobs. This is what we mean by a separable structure. Constraints are specified for each resource and each demand. The objective is also a sum of utility from allocations. This separable structure we identified naturally leads to the next question. Can we divide a large resource allocation problem into smaller problems that runs in parallel? However, we cannot just separate the problem directly. The challenge is resource and demand constraints are interdependent. These constraints are entangled across rows and columns, so one allocation affects all the other. For example, if we assign more GPU A to job 1, then the other jobs have to receive less from GPU A. This change then propagates, further impacting other allocations. To tackle this challenge, we need to decouple these interdependent constraints. Now let's look at the optimization form of the previous example. We start with the allocation matrix X, where the goal is to maximizing the total throughput with per resource constraints on the rows and per demand constraints on the columns. To decouple the constraints, we introduce a copy of the matrix called Z and move the demand constraints to Z. We also add one more constraint to keep X equals to Z. So the transformed problem is still mathematically equivalent to the original. Now the resource constraint stays on the rows of X, while the demand constraints are on columns of the Z. With this setup of X and Z, the reformulated problem naturally fits the required form of ADMM as presented here. ADMM is short for alternating direction method of multipliers, which is a classical constraint optimization algorithm. In this example, the total throughput can be viewed as fx plus gz, and the constraints are all linear constraints on x and z. ADMM algorithm solves such problem in two steps. At step 1, it incorporates the constraints into the objective, so the problem became unconstrained. This step introduces a Lagrangian multiplier term, as well as a quadratic penalty term from the constraint violation. This gives us a so-called augmented Lagrangian. At step 2, ADMM optimizing x and z in the augmented Lagrangian alternatively. It starts by optimizing x while keeping the other variable fixed. Then it's optimizing z using the previous result. After that, ADMM updates the Lagrangian multiplier and starts the next round. Since the algorithm alternates between optimizing x and z, let's take a closer look at the optimizing of x first. And the optimization of z follows a similar process. When optimizing x, the value of z is fixed. This means all the demand constraints on z no longer affects the optimization. We can also see this in the allocation matrix X, where the per demand constraints have disappeared. So overall, the constraints have been decoupled during ADMM alternating optimization. Now we have decoupled the constraint. However, optimizing the large X is still slow. So the question becomes how to decompose this large X into smaller pieces to solve in parallel. After we take a closer look at the augmented Lagrangian, we found something useful. First, the objective is separable. The total throughput is the sum of throughput from each GPU type. The term from resource constraints is also separable, as it is a per resource based defined for each GPU. Even the term from x equal to z turns out to be separable, as we can rewrite this as each row of x equals to its corresponding rows of the z. Since all these terms are separable, we can now decompose the large x into per resource allocation, which one row for each problem. And because these problems are independent, we can solve them in parallel. A similar decomposition also applies when optimizing z. To wrap up the design, DeDe decouple and decompose this problem, separating the resource allocation problem into per resource allocations and per demand allocations in parallel. These two allocations are performed alternatively across iterations. With the DeDe design, our next step is to implement DeDe for real use. DeDe builds on convex Pi, which is a Python-based modeling language for convex optimization. DeDe leverages its powerful problem compilation. DeDe also achieves its real efficient parallelism based on the Ray library. This low-level framework is highly optimized and used in all our evaluation. At the same time, we also build an easy-to-use API aligned with convex Pi syntax. The performance enhancement of these high-level APIs are underway in order to support more complex problem formulations. We implement DeDe as a Python library at high level, which can be easily installed through pip install DeDe. So here is a quick example to show how it works. First, we import DeDe. Then we create a non-native allocation variable for n resource and m demands. Next, we define the constraints. For example, we require allocation on each resource and each demand to stay below 1. We also specify an objective, say maximizing the total allocations. Once we have the objective and constraints, we construct the problem and call solve to get the result. As mentioned, our interface is largely aligned with convex pi syntax. One difference is that we need to specify the resource and demand constraints separately. And since our solving process is in parallel, we may also specify how many CPU cores to use. If we don't, it will use all available cores by default. This is our high-level API. On the other hand, the low-level API gives the user more control to manually specify the augmented Lagrangian in each per resource and per demand problem, but we are not showing it here. We evaluate several popular resource allocation problems. Here we focus on cluster scheduling problem as we saw earlier in the example. To do this, we use the Decouple scheduling simulator along with the real throughput data. In our simulation, DeDe allocated 2,000 jobs across 16,000 CPUs and GPUs. The goal is to maximizing the proportional fairness in the resource allocation. As a baseline, we compare against the exact solution computed by a popular solver, which models the problem as a convex programming. This is more difficult than the previous example, which involves only linear programming. Here is a demo to compare DeDe's runtime with the exact solution. DeDe is on the left and the exact solution is on the right. We can clearly see DeDe runs much faster. In scheduling round 1, DeDe is 65 times faster. In round 2, it's 61 times faster. And in round 3, it's 66 times faster. Now we look at some statistics and the solution quality. In this figure, x-axis is computation time in seconds, and the y-axis is a normalized proportional fairness, which represents the allocation quality. We see that DeDe achieves a fairness score of 1.1 in just 5 minutes. In comparison, the exact solution is 60 times slower than DeDe. Meanwhile, the objective it achieves is surprisingly worse than DeDe's. This is because solver fails to reach optimality due to the large problem size. We also compare DeDe against POP from SOSP21, which randomly splits the problem into concurrent subproblems. Concurrent subproblems, but POP runs in simulation without actually using multiple processes. This means it avoids a lot of system overhead. Compared to DeDe, POP achieves lower fairness and it is twice slower. For fair comparison, we also implement a variant of DeDe called DeDe star based on a similar simulated parallelism as POP. Without real system overhead like cache thrashing, DeDe star runs twice faster than the regular DeDe. Apart from the cluster scheduling, DeDe is also faster and better in other resource allocation problems. We showcase 2 additional examples. One is traffic engineering, which allocates 3 million search traffic demands to over 8,000 network links. The goal is to achieve high network utilization. The other is load balancing, which allocates 2,000 data shards on over 200 data servers to balance query load in a distributed store. In both examples, DeDe is over 80 times faster with up to 10% of better allocation quality compared to the exact solution. DeDe also outperforms POP in both in speed and quality. In summary, DeDe scales resource allocation by decoupling and decomposing the problem, turning it into alternating pre-resource and pre-demand allocations without compromising the solution quality. DeDe is open source on GitHub and can also be easily installed with pip install DeDe. If you have an resource allocation problem of large scale, DeDe is likely to help accelerate it. Right now, we recommend using the low-level API if you would like to give it a try, but we are actively improving the performance for the high-level API. Thank you for your attention, and I'm happy to take questions.